All right, welcome to geology, everybody. Sedimentary rocks. Sedimentary rocks. I guess I said it funny. So, if the three geologists we talked about in the first video were sitting around the campfire arguing about why theirs are the best, the sedimentary person would say, like, you've got, like, very literally, like the pages of a book, right? Like, layer upon layer upon layer. You've got a laid down history of former environments of this planet. I popped up the Grand Canyon page. There's a grander example, right? Layer upon layer upon layer upon layer, each one like the chapter of a book telling the story of a short segment of Earth's history. Pile a whole bunch on top of each other, you get a pretty good book. And then take these rocks and match them somewhere else and figure out what maybe was on top of this in the past. And you get a very long story figuring out the history of the planet, right? Especially the history of life on the planet. This one is from down near Cooperstown somewhere, as was this rock, where you can find fossils. So you're getting a history of the life embedded in it. Because what is a sedimentary rock? That's what we're here for, right? It's one that is made by sediments. Let's start there, right? So it's made from sediments in a very basic sense. There's some slightly different things we got to get into, but that's the basic sense of it. So put yourself in your head, put yourself standing on a beach. What are you standing on? Most likely sand. There's cobble beaches too, right? But let's put yourself on a sand beach somewhere and just picture where your feet are. That is sediment. So if you can in your head just like play that tape forward, if that sediment were to get preserved underneath other sediment, continually get buried and buried and buried, compressed into a rock, you've got yourself a sedimentary rock that used to be a beach. So you can like pick up that rock and know that environment. Let me grab one other. So here's a piece of white sandstone. Where do you see white sand today? Like think like a Corona commercial. You know what I mean? Think like tropical beach. Very nice, right? But you can find rock like this in upstate New York, which is not currently the kind of place where you're ever going to find a tropical beach, right? But that's what's kind of neat about these is if you can picture this environment, you can then basically recreate the past from that chapter, from that little page of that book, that one layer. You can recreate what that environment was. I know because of the nature of this rock and that I've played with these things for enough years that this is coming from kind of a muddy, just offshore environment. I can like hold this in my hands and picture the environment from hundreds of millions of years ago. That's why they're pretty neat. So all we're going to get into, hopefully a little shorter and easier than the igneous one, is what is the deal with these rocks? What are the three basic types that we can classify? And we'll move on. All right. So at the end of the day, what we got to have is from the other three, here's another version of this rock cycle. At the end of the day, you take any of the three rocks that we're going to study, for this to form, they've got to get to a point where they are getting broken down into sediments, into bits, which means they got to get up above Earth's surface, right? So this rock cycle is kind of unique and cool because they put that on here. So they say whatever kind it is has to be uplifted into an outcrop. And by outcrop, all we mean is like where you can see rocks. If you're driving down the highway and you can see rocks, or you go to, this is Salmon River Falls up near Pulaski, you can see rocks. That's a rock outcrop, right? So if you're somewhere where any one of these three are exposed, they're going to start getting beat up by weathering erosion, which breaks down the rock into sediment and takes that sediment and moves it downstream. We're going to be doing that in this course too, but we haven't quite gotten there yet. Let's just say, okay, yes, that's a thing. Weathering and erosion will turn those into little bits, which we call sediments. That sediment then is going to land somewhere. So again, picture a beach. Where'd that sand come from? It had to come from somewhere else, get transported there, and then deposited and dropped off. There's a lot to that. That's a loaded sentence, and we will discuss that in this course. But take it for what it is right now. Yes, a bunch of sand lands on the beach, and that's it. If you can take that and go bury it, compact it, cement it, you can turn yourself into sedimentary rock. So most of this is right out of your chapter, honestly. I almost just used the chapter, but here's a brief little note sheet if you want to use it. So what areas might we see? What are like the sedimentary environments? And again, what you would look for within that is what am I seeing? What signs do I have within this rock that let me know what that environment is? Then you can read the past like a book. Let's do the three basic types of sedimentary rocks. Clastics. So what we got here, these would be basically like what I just explained. And you might say, well, you're just saying the same thing twice. And yes, I kind of am, because clastic sedimentary rocks are kind of the classic ones. They're the ones that are very easy to picture because they are made from lithification of sediment. All right, so here's that process. Clasts, which is our fancy name for bits, that's why we call them clastic rocks. Bits of other rocks, sediment, are dropped or settle out. They land somewhere in some depositional environments. As more of them get on top, they get compressed and compacted. And as that happens more and more, plus liquids that are in there that are seeping through those pores can leave behind mineral cements that can act as kind of a cement, right? Or a glue to stick those bits together. So this is sandstone. I mean, I can feel the sand on my desk because it comes off, but there is a mineral cement that's holding those sand grains together. That's why it doesn't just peel apart like a chunk of sand. That's what that process is lithification. So how we then subcategorize those are by what are the bits themselves, what are the clasts, what is the sediment, and we can go from by basically with size and with organization. So go from smaller to bigger. This again from your book roughly goes from smaller sediments to bigger sediments, and then especially when we get to these bigger ones, we can also talk about organization being, is it made of all one size particle? Like this sandstone is made of pretty much just sand, just the same size particle, or like a conglomerate or a breccia can be made of pebbles and sands and silts, like more of a mashup of different size particles. So check that out in brief. Get a little comfortable with those. This big scary looking thing, don't panic about. I looked for a couple versions, and this is like an official version, so I figured why not? Let's throw that one on there. Here's what we would have for officially particle sizes: clay, silt, sand, pebbles, cobbles, boulders. That's going from smallest to biggest. Basically, so out of all this madness, if this is intimidating to you, don't panic. This column right here is our sizes. Everything to the right, don't worry about. It's kind of neat if you check it out for a minute, but and then we'll do size-wise millimeters. What are the cutoffs for those? So in other words, the difference between what we would classify as a piece of sand and a pebble is right there, size-wise. Sorry, I can't highlight in that. And then sands, we could say you go from fine sands to coarse sands. If you've been to a lot of beaches, you've probably experienced that. That some of the grains that make up that sand feel a little coarser or larger. Or depending on, I mean, if you're on campus, go down there and you get to like a cobbled beach, right? That's where the environment there is so high energy that it doesn't let sand sit. The sand gets pulled away, carried somewhere else, leaving only the cobbles behind. So yeah, I mean, particle sizes, you can roughly use that, and that is going to be what determines what kind of rock it makes. Sand makes sandstone. Silt makes siltstone. You know what I mean? It's fairly easy to break down off of that. So there's clastic. There's your very basic kind. Let's just rewind to the beginning and think about this. We can use this as this picture for two purposes. We've got old sedimentary rock here, and we've got a modern day, this is last winter, river flowing over the top of it. So this river is breaking down this cliff, as is like freeze thaw and other things, turning it into sediment. That sediment is washing into the river, and it goes down through Pulaski out to Lake Ontario, right? That's the process that is going to bring sediment somewhere to land somewhere that could eventually form a clastic sedimentary rock. But now what I want to do, if we switch gears to chemical, which is our next one, is talk about how it's, in a sense, the same exact process. This river may not, it's not salt water, right? Do we know the difference? I wish I was with you guys often. But the ocean is salt water. Hopefully we're comfortable with this. And up here is fresh water, right? So I would say, yes, this is fresh water. It's not salty. However, If it's washing over anything that's soluble at all, like salts, limestones, things like that, it will have some of that in it. It really, you could say it's a very, very, very weak saltwater solution that flows down towards the ocean where it accumulates. The salt gets left behind when the water evaporates and comes back up through the water cycle. And it happens over and over and over again. So is this salt water? Like, no, we wouldn't call it salt water, but is it really, is there a tiny bit in there? Yeah. So what can happen, and a good demo of this, they put it in your book, or I got it right here, would be make some salt water, just mix some salt and water together, and leave it sitting in a little dish and see what happens. I thought there was in here. Sorry, I'm sure this is fun watching me scroll through your chapter. Well, anyway, here it is in real life. For a separate experiment we were doing in this class, I made some salt water. And what has happened as it's evaporated is that all these crystals have formed. Solubility wise, there's only so much of the things that make up salt that can be in water. As it evaporates, that gets to a maximum, it's saturated, and it's got to turn back into a solid. So do this in your head, just like the sediments. If you can picture sediments washing off this cliff, going down river and landing somewhere, now just do that with ions. And I know that's harder to picture because they're like dissolved in water. But as they're dissolved in water and they get carried downstream somewhere, eventually there's going to be a place where water is going to be in like an evaporative environment. Where if, especially this happens in like any place where pools get isolated, this can happen like, so go to like the Great Salt Lake. Where if water evaporates off, then the concentration of those sodium and chloride ions in there get to a point where they can no longer be in solution. It's saturated, and it will turn into a chemical sedimentary rock, like the outside of this. This is just salt. I took salt and evaporated it. I'm sorry, I took salt and dissolved it in water, and now the water is evaporating and the salt's left behind. That's what a chemical sedimentary rock can be, like an evaporates. So the most common type forms from, this is the fancy term for it, it's a precipitate from solution. And if that vocab's too intense, the solution, salt water is a salt solution. Make some Kool-Aid, it's a sugar solution. You ever like have a drink of some type, fruit punch, something, and leave it on the counter too long and the water evaporates off and you get that like sticky ring on the bottom? You just did the same exact experiment. You let the water evaporate off and you chemically reformed that sugar loosely as a rock, right? If this happens in large scale, you get yourself big layers of salts or of other evaporates. This can happen with limestone too. Here's, in fact, again, down this field trip I did last summer outside of Cooperstown. This is what was considered by the people running that trip to be the youngest rock in New York State. It's the water that's seeping up through the ground there is lime rich. It's coming through limestone. It's got the calcium and the carbonates in it, right? And as it thins out on the surface and that water evaporates off and the concentration of that gets too high, it forms this rock right there. Brand new chemical sedimentary rock forming. Like, I mean, if we could really slow down time, look at it, it's forming today, right? It's consistently forming and has been forming in this environment. And then I only did this picture because it's like right there, but this layered rock back here is older rock for sure, but like kind of attached, almost like oozing out of the wall in this area, and all along that whole side of the river would be this younger rock. And they talk about this one specifically in your book with tufa. It's a tufa, is that rock, or if you've seen stalactites, stalagmites, similar idea. All right, so let's do the coal stuff, the organic stuff, real quick. And just to make sure we're all on the same page, I know that those feel like two separate things, like accumulation of sediment and the accumulation of ions as a precipitate, but they certainly belong here more than they would like igneous, right? They don't come from magma or lava. We haven't done metamorphic yet, but they don't come from something being mangled under heat and pressure. Sedimentary is the best place for them. So let's do that same process again, Only now have it happen with organic materials. Um, made from accumulation of, organic matter. Well, I did pull these out, but I think it's probably better just to use these pictures, because I think by the time I hold this up to the camera, they're just going to kind of all look the same. But take a swampy area where plant material is dying, and it's the right kind of one. If there's continuous flow here, that can break down. But if you get the right mix of water and the right like kind of lack of oxygen, it can accumulate rather than break down. And as it does, you get these organic layers within it. So put it under a little. So if you've ever been into like a boggy area, a swampy area, that could be like the very, very, very early stages of this. Preserve that for what we won't be able to see in human lifespans, because our lives are too short compared to the time that these processes take to happen. Is that those could get more and more compressed and produce peats. If I do pull this one out, the peats, it's pretty hard, but maybe gives a little bit. It's extremely light for what we would consider a rock. A little bit of give, and it's like if you could take a whole bunch of swamp material. This takes time, right? But if you could take it and squeeze that water out and really like a charcoal briquette, take all of that available bioenergy and smush it in, that's what you got. People do harvest this and use it. But where it gets to be more and more valuable then is under more and more pressure, you can get yourself up into getting higher and higher grade coal, up into like metamorphic forms of it. So more pressure on top of it, more pressure on top of it, more pressure on top of it will get you harder and harder preservations of those. All right. The map didn't come up. Let me pop the map on here quick. So where in New York? I wanted to have that on all of these. We talked about the igneous not being super prevalent, a little bit over here with the Palisades and a couple other very specialized random spots. Sedimentary, really easy to find it. It's almost everywhere in New York. In fact, if we go and circle in a brighter color, if we go and circle the Adirondack Mountains and say, not that, and some regions through the mountain ranges that exist between the border over here, we can pretty much say everything else is sedimentary. Certainly Oswego. The rest of that state is all layer upon layer upon layer of sedimentary rock. This bedrock map shows us that we're dealing with like Ordovician age rock here, and they get younger and younger and younger as you work your way down. What you have to picture is that this is exposed, this is lying on top of that, but like, so this rock that Oswego's on would be down underneath the rock where Syracuse and maybe South Rochester are on, and then that is underneath the rock that tops, especially the tops of the valleys through the Finger Lakes. But hey, let's not overcomplicate life, right? Most of the state, excluding the mountain ranges, we'll say falls into that section on sedimentary rock. I'll stick this map in the notes before I post them for you. Is there anything in the book that we want to hit before we go? There's the like that can be an evaporite environment too in British Columbia, so it doesn't necessarily have to be like tropical reefs for this to take place. Hey, there's the salt. Make an evaporite. Make salt water. Put it into a dish. Let the water evaporate. You got salt again. Like it's not that. It's almost like deceptively simple how you form these chemical sedimentary rocks. I just wanted to say you don't have to necessarily, we did some of that time stuff already in other units. Don't get too bent out of shape about the bedding stuff. It's more hints as to how you can interpret the history of the planets. But I won't make you go in like super specifics on those on the tests. Fossils is a big thing to note. I'll do a video at the end of all three. There was a section on those notes that how do you tell this is this kind of rock versus the others? But fossils is one of the big giveaways. How do you get fossils? The only way it's going to happen is if they get buried in sediment. So it's a pretty good giveaway that you're holding onto a sedimentary rock if you find fossils into it. The stratigraphy stuff too, I'm straight up going to leave out. So 9.6 you can cross off as you're working your way through the book. I'll leave out of the tests. If you're a major, it might be a good idea to tune into a little bit of that. Get yourself acquainted. more of it will be coming for you soon. All right. And the intro, we'll use the outro. Why are they cool again? This says right here that like this black layer about halfway up is a coal seam, and it tells us that at the time it was swampy. Like we said, if you can picture a swamp and see that being compressed, you've stood near a swamp. There it is again, but this is a swamp from, in this case, Mesozoic, a long, 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 long time ago. And that's why these rocks are cool. They are chapters in the book of Earth's history. Hope you're doing well, everybody. We'll see you soon for Metamorphic.